My name is Lo. Today, I would like to share about smart manufacturing with Cognex Deep Learning solution. Look at the fancy videos in the page. I believe you cannot wait to know more about Cognex Deep Learning. Cognex, we are a leader in the industry of machine vision. Here are some basic facts. We have been in the business for over 40 years. We have more than 25,000 customers, and last year, we generated over 800 millions in revenue. We have offices in 20 countries, working with 400 plus partners, and until now, we have shipped more than 3 million systems worldwide. And machine vision is the technologies that give computer the ability to see. A vision system operates like your vision does. Your eye is an optical device. It captures information and sends it to your brain, which makes sense of it. In machine vision, a camera and a lens capture data, which is sent to a processor where vision software interpret it. So you have heard about machine visions. So let's talk a little bit about where those products are used. The answer is just about anywhere. Vision allows you to monitor and manage your production line to make sure it is done correctly. This helps you to reduce cost and error in your manufacturing process. When we look at smart manufacturing, it is 4 industry revolution. First revolution, we started to change from human energy to the other power, water and steam. Second revolution, we changed to electric energy to increase the volume or yield in mass production. Third generation, we use robots, conveyors, and motors to improve the speed. We call this automation. These 3 revolutions focus more about the human physical ability. Smart manufacturing equals to Industrial 4.0. So Industrial 4.0 focus on connectivity and cognitive ability. We try to collect more data, but most importantly, we use the data. But who is the biggest driver? So when we look at these pictures, everybody know it. Of course, from 2020 to 2021, the biggest driver must be the pandemic, COVID-19. These are the news I found from the internet. It has given biggest hit to SMEs, which will need a lot of time to recover. And starting from May this year, due to high and growing new cases, the government has implemented a few MCOs to contain the spread of virus. So everybody cannot go out. In June, Malaysia implemented total lockdown. A lot of workers were not allowed to go back offices. A lot of factories shut down, even though now the control is getting lesser. Everyone get back to office, but a lot of concern with us. So I believe this is the best inflections for everyone to think about smart manufacturing. We can try to convert more manual work to automations. And this is the example I heard. I think this is the best story to talk about the conversions. So let's hear what they say.
This is a factory producing glass lenses for the German brand Carl Zeiss. 7 out of 10 lenses made here will go to Europe. 4 years ago, the manager discovered this Chinese plant had lost its biggest competitive edge, low cost of labor.
In 2012, the Zeiss Group informed us that labor in China was twice as expensive as in Mexico and 4 times that in India. We were very surprised at this huge gap and started to think of how to improve productivity.
Then Zeiss made the change. Let's continue to hear what is the result.
The factory introduced new automatic machines and techniques called freeform to replace humans in manufacturing. Now the machines can take care of most of the major steps, from pasting protection films, cutting shapes, polishing glass, and packaging.
Wow, this is an awesome result. I think Zeiss feel grateful because the change started earlier. And COVID-19, I don't think impact GIS so much. So in automations, machine vision works same as human eye. In this video, you can find this robot trying to open the knot, but it failed. Why? The motion is 100% right, but it did not do it at the right locations. Because the robot just don't install the machine vision, so it cannot know. What does machine vision do? So from the upper left, it verifies that the ceiling and also the water level of the water drain. Second, in the upper right, it inspects class film filter to make sure that O-rings is present and fully seated. Lower left, it verifies all holes has been punched through on a cascade. Lower right, look for presence of blue quality control mark. You can see it, right? So on a front wheel bearing assembly, if QC mark not found, it indicates that assembly needs rework. So how do we do to solve the normal vision application? Usually we have to inspect a part by looking for the good fixture first. Second, apply the vision tools like barcode reading tools to read the data matrix code, OCR tools to read the print, or the next, finally, we use a measurement tools to measure the width of the parts. So you must understand, traditional tools, this is the rule-based system. We must use different kinds of vision tools to combine them like contrast tools, pixel count, logs, contour, edge, decoding, and so on. You need to follow the sequence in this way. Conventional vision system has limitation to solve these four kinds of applications like defect detections, material classification, assembly check, and challenging OCR. Conventional vision system started to face performance issues. So usually we still need human inspectors. That is the biggest challenge and barrier to go smart manufacturing. And finally, we have some answer for you. So deep learning is the answer to them, help us to convert more application with better performance. But how does deep learning works? This approach is different than traditional machine vision. This approach is mimicking the brain. We teach by example. So if I want to let deep learning to recognize a house, so at first, I will just provide different images of houses. And deep learning, or this small little girl will try to generalize and conceptualize. So this is how deep learning works, and he will know. So what is a house? In these pictures, you know deep learning is a core part of AI technologies. So it focuses more in cognitive ability like human. But deep learning, we have to learn from a large amount of data and allow machine vision to adapt and continuously improve the program. So in short, it is human-like, it can do self-learning, and most importantly, very powerful. So how does deep learning train? So all vision tools follow the same fundamental flow. So first, we collect images, good and bad, and we have to label them consistently. This is the most tiring job. But after we train, you will find, okay, this is so easy and we can validate the result. So 3.0, we can help to convert some routine work. This is how is it? But coming to deep learning, we can provide cognitive abilities or predictabilities in production flow. This aligns the direction of Industrial 4.0. So deep learning falls into this part. Then coming to automotive applications, I have tons of applications to share, but I just summarized in this page. First one, we can do cosmetic inspections, engine blocks, ceramic spark plugs, or printed dashboard, and so on. We can do mesh and textile inspections. We can check the structures, we can check the fuel filters and seatbelts. And coming to kitting, we can do spark plug tray or door handle checking, assembly check to make sure right product at the right positions. This is good for seat trim or covers, wire position, car and headliners. And we can do OCR to read the wing plates or the textures motor parts to read the print on them and to do the welding inspection. So these are the common deep learning application in automotive. Coming in electronics, so normally we focus those value product. So smartphone is the most application we normally do. So module, we can check the battery scratches. We can check the headphones and the speaker mesh. And we also can check if there's a dent on the housing. And we can do pre-assembly check to make sure all the components present or LED inspections. For PCB, deep learning is very, very good to check the component present absence, especially a board, it contains hundreds of components. And deep learning, we can train it easily. And we can do pre-assemblies, debris detection, and last but not least, solder inspections. So these are normally we handle in consumer electronics. And some example to give you more understandings. So I want to share with you first application. It is about medical school inspections. At the top side, so there are good screws. And we need to train like some images. Let's say I capture 100 to 200 images. Then when it comes to the production, so if you try to detect if any anomaly on the samples, so the bottom side shows you, it detects some dent or some scratches on the screws. And other applications we can do is to monitor the process. So this is like we try to check the flow of the solders from left to right, up, down, to make sure this is done properly. And you can find the solder never be consistent because this is a liquid. And only deep learning we are able to handle to really to make sure we can detect the process. Or some application to check the CAD ingredients. When we try to rotate or we try to stir the mixtures, so you can see this is all the good conditions. And when coming to some problems and some foreign material like fell into the mixtures, so we can see by using deep learning, it detects even though just a small little like debris or a small little foreign materials, we can detect and tell the system, oh, now there is something wrong. Or we can do classification for food. This is a good example. We can try to train different parts of chickens. Then after that, deep learning system can tell you, it doesn't have to be the same for all the pictures, but most importantly, we train another sample and the system is able to tell whether this is a chicken breast or this is a chicken wings or flex or the type. So this is interesting. So there are a lot of applications we have. And coming to trade shows, and from here, I want to show you this application. Why? Because fish counting always, this is very challenging because fish is a live thing. When we swim, so you have different orientation, different patterns, and you have different size. But deep learning, after we train like 100 samples, so we can detect all the fish without any problem. So this is a performance. This is how good we are able to handle it. And to make this work, this is the basic deep learning architectures. So at first, we need algorithm. Second, we need GPUs as a processing power. And last but not least, we need a lot of image to train to make it work. And in deep learning, you can think that the general model we use is from convolutional neural networks. It consists of thousands of classes, and each classes is a layer of neural networks. So to train it, we need to train 1,000 classes with a lot of images. It can be millions to make it stable. So what makes Cognex Deep Learning unique? It is optimized for machine vision and specifically for the real-world factory environment. We can train on limited set of data like 100 to 200 images, where others require millions of images. Then we can train on a single PC with GPUs. Then others might need supercomputer or mainframe to make it work. With our tools, we don't need a PhD to configure and manage, because there's a lot of graphicals. As long as you are a Microsoft Excel or Microsoft Word user, you can handle it without issues. And it is also bundled with Vision Pro traditional machine vision software, so to solve different kinds of applications. So I would say this is the most powerful software you can see in the market. We try to put this kind of system in our smart cameras. So let's take a look. I have a video to introduce this camera. We call it D900.
The Insight D900 is a standalone vision system running Insight ViDi software designed specifically to run deep learning applications. This embedded solution easily solves applications too difficult to program with traditional rule-based machine vision tools and provides reliable, fast, and consistent results not possible with human inspection. Applications are deployed on the Insight D900 smart camera without the need for a PC. Using the familiar and easy-to-use Insight spreadsheet interface, it helps simplify application development and factory integration, making deep learning technology accessible to non-programmers. The Insight D900 has both 2.3 and 5 megapixel options, allowing you to choose the right resolution for your application. Advanced image processing with HDR+ creates a more uniform image on a single capture, ensuring every detail is visible, even under challenging lighting conditions. The Insight D900 is rugged, with an IP67 rated housing. It's able to withstand even the harshest factory environments. Field-changeable lighting and optics provide users with ultimate flexibility to customize the system for their application. Example-based deep learning allows users to automate inspections not feasible with standard rule-based machine vision. Applications like defects detection can be programmed using only good read images, drastically reducing the setup time needed to get the system up and running. And because the training models use multiple images, ViDi can handle variations in the targets, as well as changes in lighting and camera perspective. Character recognition can be easy to do with rule-based machine vision, as long as the characters are clearly printed on plain backgrounds. But if characters are skewed, or if codes are imprinted on confusing and complicated backgrounds, standard vision can't solve the problem. OCR, especially on hard-to-read and obstructed codes, can be easily done with deep learning. Insight ViDi is preloaded with a font library right out of the box, and can be further refined on the factory floor. Manual inspection was once the only practical method for assembly verification. Parts can have too much variation, and frequent production line changes make it difficult to reprogram a vision system quickly. But because ViDi's neural network uses multiple images to create a working model for each component, it can handle part variation with ease. Plus, operators can use ViDi to create a component library and use that to create custom layouts right on the factory floor, making new line configurations quick and easy to do. Deep learning is changing what's possible in factory automation. The Cognex Insight D900 is making deep learning-enabled machine vision more accessible and easier to implement than ever before, enabling users to further improve quality, efficiency, and throughput in their facilities.
Wow, this is a very good introduction to our deep learning system. So I believe I have some experience with customers when coming to deep learning applications. They told me they always need to spend a lot of time to source the camera to get the system run. Easily 1 to 2 years. In Cognex, so we would like to make this process faster. So that's why I would say deep learning with smart cameras. So this should be the right answers. So today I'm not in MetaTech, so I cannot show the live demo. So I would like to share 2 videos. So the first one is about the plate and tube identifications. So this application, we try to use the deep learning to recognize whether any empty cat tubes. So the blue one is a good, then the gray one shows there's no cat. Then we try to change to other one, which is in different color. We can detect those empty cube without changing the job file. This is all in one. And coming to trait recognitions, so we can recognize this is the type 1, or we can compare side by side for a 24 pocket model and the 12 pocket models. And how about the color change? We try to change it to other materials. So over here, it also shows you another very important point. So deep learning, this is so robust, we don't need a controlled environment. So we just use a normal light in a normal environment, so we can actually detect them, and the result is awesome. So the last time Ruby system, this is so difficult, and now can you see this is a live demo. We can show with a normal environment, and this actually can give you a hint. So in future, so we are easier and we can actually convert more applications. It's not difficult to use. And the next one, okay, after I've removed these two trays, so the last one. So a big one with all kinds of product. So deep learning also can recognize, even though there is a mix with different color, different size and model. Wow, this is really impressive. And to show this is not a magic, we try purposely move the locations. Can you see the detections, the result is still good. And the next one, okay, is a live demo for the challenging OCR applications. So you can see how my colleague demo this.
Down the ROI for just the characters. And with the transparency, I can start doing interesting things like bending it and changing the scaling, changing the shear and the aspect ratio of the characters to prove that the video retool is very robust against those changes. And just to prove that that's not black magic, what I can do is I can cover up some of these characters to show what happens when a tool can't read characters and they're totally just not visible to the camera. And for the sizzle part, we can start messing with the background, right? So let me just increase my exposure real quick. We'll want to start the demo around 0.4 probably. And I can introduce this carbon fiber business card and show that as the background changes pretty drastically, we still get good read performance. I'm just going to throw a different transparency into there to show a different one. So that's pretty neat. I can do some other interesting things like throw in some bubble wrap, make the background kind of challenging. Let's do that. Actually, let me just decrease the exposure now and make that more interesting. So, in fact, I can read through the bubble wrap, so you can see how well the video read tool performs when there's a ton of variation on the characters. Oops. Some other things I can do, introduce a really varied background like this one. And again, the video read tool can perform pretty well on that. So then if the customer is interested in seeing how that was set up, we can go into Vidi Suite and show them another interesting detail.
Yeah, that's all for my live demo. From here, you can find D900 is a killer product for this kind of application, challenging OCR or present checks. After the live demo, I would like to share a 10 minutes video about the defects detection tutorial. Then you will know how to train a system.
Hi, my name is Bart Piela. I'm a technical marketing specialist here on the deep learning team at Cognex. Today, I'm going to take you through setting up the ViDi Detect tool. So in terms of my setup here, I have the D900 and it's hooked up to 24 volt power and the Ethernet cable is hooked right up to my computer. My computer is GPU enabled, which allows me to train the deep learning tools. And the other thing I have here is a USB dongle, which is what has our security licenses on it. In the application we're going to tackle today, we have a text style. So this is what the good text style looks like. And here's what some defects look like. And the objective of the application is to use the ViDi Detect tool to pick up these defects. So with that, I'm just going to jump right into it. The first thing I'm going to do is put my good part under the camera, and this camera's already been focused and all the image formation is set up. So all I have to do is, give it a couple triggers. We can put it in a live mode and show what the textile looks like. But the first thing I want to do is I want to collect images of both my good and bad parts. So I'm going to use the film strip down here. I'm going to click this record button. And with that, every time I trigger, I'll get a new image in my film strip. So I'm just going to go through that process for maybe 10 or 20 images of good parts. And you'll notice that I'm rotating with every image, because in this mat application, basically the textile pattern can appear in any orientation. And so once I have 15 or 20 images of that, I'll also want to capture some images of my defects. So here you can see what a defect looks like. I'll do the same thing here. I'll capture a couple different defect types. Let's get some of those small ones in there. Great. So now I have a good representation of what good and bad look like in my application. The next thing I'll want to do in this film strip is just to append some descriptors to my images. And so what I'm going to do is I'm going to select this first one. I'm going to scroll all the way to my last good image, which is right here. And I use the Shift key and click, and that'll select those images. And if I right click, I can rename selected frames, and I can prepend a string. So I'm going to call these good, because this is all my good images. And you can see that that file name was added. I'll do the same for my bads. So I'll select all my bad images, right click, rename selected frames, and I'll prepend the word bad here. And this will be useful here in a second when we get to the Vidi tool. So now I'm good with my images. The next thing I want to do is I want to drop in a Vidi tool into the spreadsheet. So that's as easy as going over to the toolbox here, selecting Vidi detect, dragging it over to an empty cell in the spreadsheet. And just like that, we can open up the Vidi editor. The first thing I want to do before I do that, though, is to set the region. So just like all the other tools in Inside Explorer, the Vidi detect tool has a property sheet where you can change some settings. And I'll set my region. So this is my inspection region. I'll set it to be most of the image. I'm going to focus on the middle of the image. So once I have that set, I can hit that green checkbox. And now I'm ready to go into the Vidi editor. So clicking this button will open up a new tab for me in the interface. And to anyone who's used to working with Vidi, this is basically exactly what Vidi looks like, except now it's within the Insight framework. So now what I want to do is I want to grab all these images that I recorded. I can turn off that record button before I forget. I'm going to grab all of these and just drag and drop them right into Vidi. And for the time being, I'm done with this film strip, so I'll close that out so I have more screen space. And you can see that that region that we set in the spreadsheet has already been applied. The other thing you'll notice is that up here, I have the file names. So you can see that that good and bad naming is already in Vidi. So I can use that to my advantage when it comes to labeling images. I can use a single quote syntax and type that string that I'm looking for, which is capital G-O-O-D. And what that'll do is that'll filter out and display in this pane only those images that have that file name. And so this makes it really quick for me to label these images as good. Let's bring that over here. So I'm labeling these as good. And so you'll get that green checkbox or that green flag up at the top right of the image. And I can do the same for the bad images. So just type in that bad with the single quote syntax and label these as bad. Bring that out there. And so now, with just a couple clicks, I've labeled all the images for Vidi. And so just to scroll through here, right, I have the red flags on my bad images and the green flags on my good images. Next, what I want to do is I want to set my feature size. So this is the magnifying glass, you can think of it, that Vidi looks through to understand your images. So an easy way to get a good estimate for my feature size is I can use this bubble here and I can just drag it onto the screen on my smallest defect and just approximately size it to what that defect is. And if I open up my tool parameters here, you'll see that feature size, as I adjust this, that changes the feature size parameter over here. So I'll put that back to 60. That was a good number. The other thing I can set from here is my training selection. And so what this is the split between what Vidi takes to be training information versus testing information. And so in this case, I'm going to use 50% of my images. And in the case of a video detect tool, all it's doing is taking the images that were labeled as good. So I have, let's just do this real quick. I can pull up all my good images. So I have 18 good images. And so with that 50% split, basically what video will do is take 9 of those images for training, and the other 9 will be used for testing. The other thing I want to account for is the fact that I have rotation in my application, but I don't have an example of every angle that's possible for this application. So what I can do is I can add a rotation perturbation. And what that's going to do is it's going to augment my training information to include those images at any rotation, at any angle. So what that does is ViDi is going to basically synthetically create those rotated images and train on them so that the application, the tool, the model learns what rotation looks like. And so with that, all I have to do now is click the train button. And now ViDi is going to take all those labeled images and train on what a good textile looks like. And depending on your GPU and depending on the application, this can take somewhere between 3 and 5 minutes. Okay, so now our ViDi tool is done training. Let's go through the results. So what you'll see after you have a trained tool, you'll see this border around your image, and those are ViDi's predictions for whether that image is good or bad. You'll also see a score. If you open up the database overview, you'll see this score histogram. And basically what this is showing is in green are all the images you labeled good, and in red are the ones you labeled bad. And what you hope for is you hope that ViDi can separate them by score. You have this big gap between them. That's a good thing. In this case, the ViDi detect tool, the way it works is since it's a defect detection tool, it's going to score images where defects are present. It's going to score those higher. And so if we go through and just look at all the images, let's go and find some defect images. So you'll see here, let's make this a little smaller. You'll see here that the defects are being highlighted in red. So the other thing, I can adjust this threshold here to make ViDi a little less picky about what it's calling a defect. And you'll see when I do that, it just draws the defect regions a little smaller. So I'll set those that tolerance there, a threshold there, and we'll go back to the spreadsheet. And I can put a sample under the camera, give it a trigger, and now I have a ViDi detect tool in the spreadsheet. So one really useful thing in order to get data out of that tool, what I can do is I can right click here and I can use this insert getters command. And what that's going to do, and I actually want to do that when there's defects present. So let me just put a sample with defects, give that a trigger. You can see when I click here, you get the graphics. Right click again, insert getters. What that's going to do, it's going to populate these cells automatically with all the functions that get data from the ViDi tool. So you can see here for each of those defects that I have in this particular image, I have the area, the perimeter, its location in the image. So I can use this data for other vision tools. I can use some logic on it, and I can do whatever sort of things I want to do in the spreadsheet with that information. So what we're going to do, we want to now start thinking about what our HMI is going to look like for the user in production. The Insight Vision Suite ships with 2 default web pages. If I go to web pages here, I can double click on main. So this is what the default web page looks like. It has this great space where I can put some other data. So let's go and publish some more data to this web page. So back in the spreadsheet, let's say I wanted to publish the score. So this is my ViDi score for the probability of the confidence of there being a defect in the image. So if I just right click and publish, I'll get a score here, and it'll also publish in my tags. And now if I go back to my main web page, let's pull up the tag browser. So I go to view tags, and there's my tag browser. I can search this for score, and it's going to be in here, score. It's under my inspection task in the spreadsheet, score. And all I have to do now is drag that onto my web HMI. And so now I can get data basically published to my web HMI really easily. So let's go do that with one more item here. Let's say I want to enable the user to change the graphics of the ViDi tool. So what I can do is I can go into this property sheet here, grab this whole show property and plunk it in my spreadsheet. Okay with that, and then I can right click and publish that, and it's going to be by default called show. I go back to my web HMI, and now I can search my tags for show. And in a similar way, drag and drop it into wherever I want it on my web HMI. Let's put it there for now. So the last thing I want to do, this web HMI comes with a live film strip, and I need to assign a watch cell to that. So that's pretty simple. I'll go over to my past getter from the Vidi tool, right click on that, and select watch cell. I'm going to set that as my watch cell. Okay, so with that, I'm going to go ahead and put my camera online and see how it's doing. Okay, so now my camera's online. You can see that that score is updating. Right now I don't have any graphics shown. I can pause this film strip and review the images. So let's go ahead and show some graphics. So there we go. Move this around to different defect types. Let's show some of those smaller defects. You can see Vidi's picking those up. Let's spin this around just to see how that works. Awesome. Let's go ahead and put in a good sample. See what it does there. So you can see it's passing those regions. Excellent. And I can pause on this and review any of these images if I wanted to. The other thing I can do, I can pull this up. Since this is a web HMI, I can pull it up in a web browser. So to do that, I can just go back to the shell of Insight Vision Suite and click this Open HMI button. And what this is going to do is it's going to pull up my default browser automatically with the right IP address, and we'll see the same web HMI that we set up before. So here's this, and just for good measure, we can throw this in here and show how it's highlighting defects. Okay, so just to recap on our demonstration of the Vidi Detect tool, the workflow steps that we did. First, we collected images, and then we imported those into the Vidi editor where we labeled them for Vidi so that Vidi knows what's good and bad. We set some tool parameters, and we trained the tool and reviewed the results to make sure that Vidi can separate the good from the bad. Once we knew that our Vidi tool was working, we went back into the spreadsheet and used the insert getters function to get all the results data back into the spreadsheet. Once that data is there, we can do some things in the web HMI with that data, like control the film strip or publish the score. From here, a user could spend more time with the web HMI and customize it to whatever the need is in the application. Another thing that you could consider doing is setting up the communications, whether that's to the PLC or to discrete I/O. Thanks for watching.
And the next in Smart Factory is to transfer the data. So when more and more system is implemented, we can collect the production data into the cloud. So remember, OPC UE is the unified platform in IIoTs, which allow machine and device to talk across the machine level, network, and database. Cognex product, all our product, we can handle this without issues. In my last slide, I would like to share with you what Cognex can help in smart factories. So I try to put one example in F&Bs, so hopefully everybody will like it.
Modern food and beverage manufacturers have some complex recipes to follow. Along with flour, cocoa, and sugar, manufacturers also need to mix in key ingredients like traceability, quality control, productivity, and regulatory compliance. Cognex vision and barcode reading technologies help manufacturers around the world improve product quality and their bottom line by tracking products through the supply chain, eliminating defects, and enabling automation. Visual inspection of raw materials ensures product quality. Catching defects as soon as they happen improves productivity and reduces waste. Cognex Vision is used to verify quality in real time and trigger the system to reject defective products. Cognex DS1000 3D displacement sensors find defects that are hard to see with 2D systems, measuring product volume, inspecting logo imprint, and checking for damage. The Insight 2000 looks for brightness, contrast, color pixel count, patterns, and measurement. Here it's checking for gaps in the tray to verify that it's filled properly. Ensuring products end up in the correct packaging is crucial for allergen management, consumer safety, and brand integrity. It is also the key to reducing costly product recalls. Insight Vision Systems offer a wide range of industry-leading vision tools that are able to keep pace with the fastest packaging lines. The Insight 7000 series inspects the integrity of the package, verifies the date and lot code specified by the PLC, and reads 1D and 2D codes. Dataman readers optimize traceability, which helps prevent counterfeiting and minimize losses. If a recall ever occurs, locating a specific batch is easy. Food and beverage manufacturers around the world rely on industry-leading Cognex Vision technology to optimize product quality and productivity, control traceability, and drive down manufacturing costs. For more information on game-changing Cognex solutions for the food and beverage industry, contact your local Cognex representative or visit cognex.com.
So this is my last slide of today. Thank you everybody for watching my presentations. If you have any inquiry, please always contact to our sales development leader, Ms. Yung Woon. And now we can move forward to our Q&A sessions. Hello, hi guys. So can everybody hear me? Yeah, I believe so. And yeah, finally, this is our Q&A sessions. Please feel free to ask any question you have. So the first questions. So how to submit inquiries? Wow, I think you must love our deep learning very much. So very easy. I think in the display, you can see there's a QR code. So what you can do, just scan the QR code and put all the information in the feedback forms. So our representative will reach out to you. So it's so easy. So I think second questions. So how can I start my deep learning projects? I have no experience. Oh, wow. This is also another common question because I believe most of you know about rule-based system or vision sensors. So how to start a deep learning application? So as I mentioned in the presentation, deep learning is not something we know, and it will be more on the example-based learning. So how to start the project? So always we should aim for just right project. First, not too easy, but you must justify the resources commitment. Of course, not too hard, which is unrealistic requirement leads to unrealistic conclusions, because most of the time we try to bring out the most challenging application, which is not solved for 20 years for deep learning. So I think this is not good because you just learn about deep learning. We always aim for a straightforward in the first applications. So actually, after you have more experience with deep learning, then I believe you will have more confidence when it comes to the next applications. Okay, and next one, you also need to have clear understanding of your goal. So you must really know whether you want deep learning to reduce the scrap or reduce the SKP or labor costs. These are the top three normally the goal we need to have, but you need to specify clearly. And last but not least, for the deep learning project, always we need to define the requirement, because most of the time I found customer cannot give a clear maybe acceptance criteria to the project. They just can give us a rough idea. So that is not good for the vision application, because we actually have to understand clearly, and besides, always we need to reach out a mutual agreement between the developer of the vision system and also the customers. So after we can actually reach out a common understanding and to put the more realistic requirement for the application, I think normally we have confidence the application we can solve by using deep learning. So this is how we start with the deep learning application, especially for your first applications. Yeah, I think let's move on to the next questions. Oh, with traditional vision, I know exactly what is possible or not, but how do we know really sweet or deep learning system behaves as what we want? Okay, so traditional vision actually very straightforward. We just try to dummy the images, and based on certain parameter setting, then we can know whether the system or the tools can actually do what we want. But deep learning, because when we try to dummy images, and if you're trained by using the neural networks, and we don't know what is inside the neural network, normally we can consider neural network is a closed or a black box environment. So we don't know what is inside, but this is the beauty of deep learning because there are thousands of classes, a lot of neurons doing very complicated things. But the result definitely is awesome. So you can think that it is true that deep learning does not behave like a traditional image processing tools, but there's also no guarantee that if you catch all the defects of a specific size or grade level. But deep learning, how we compensate in the advantage is that it is more adaptive to the real world condition because when it comes to application, you can see there are all kinds of conditions like variation in the parts, environment, lighting, shadow. Then deep learning, after we train enough samples, so we can easily deploy to solve those applications, which is enabled in traditional visions, as I showed in the graph. So it is very essential to start with a representative set of training images. To label them correctly, most important is correctly and carefully tune the system until you achieve the result you want. So normally we will take, I would say, a few weeks to 1 to 2 months because we need to collect a lot of data, a lot of images. Then until we can achieve like 98%, but this is what you expect to see, then only we stop the training for the neural networks. So this is a little bit same like what normally we see in those AlexNet or general convolutional neural networks. But Cognex, you'll find that okay, our system, it will be much easier to train because we just need a small set of data for hundreds to a few, maybe hundreds, I would say from 1 to 200 to 500 images, then we can reach out to the result you need. Yep, that's all for these questions. Let's carry on. How fast can the smart camera achieve in the inspection time? Oh, great questions. I always hear this question after I present like D900 to the public and also my customer. Because like this camera, I would say this is the best and fastest smart camera Cognex ever built. So there are multiple core processors and also we have inference engines in the camera. So the speed wise, I would say in the market, in terms of the same performance, same speed, so nobody should be able to beat us. And for this system, normally, okay, it tends to like get 300 parts per minute for a typical application. And with the latest tools we have, EL classified, we are able to achieve easily about 400 to 500 ppm. This is a new tools we have, which is the next generation of deep learning tools in our D900. Of course, let's say you really need something which is faster for F&B, for pharmaceuticals, or for packaging. You need to achieve like 800 ppm. Don't worry, Cognex, we have solution for you. So the idea is move forwards to our PC-based solution. Then it depends on your like hardware, like the PC specs you put it in. So you can put in the best like GPUs in the market. It can be the RTX 3080s or Tesla V100. So it can actually increase a bit. So actually we deal with a lot of applications, so we know what you need. Okay, that's all for these questions. And next. So what it's necessary to perform a proof of concept of feasibility. Wow, that means everybody are very excited. You want to try this software. Lo, very happy to hear this. Okay, so normally, okay, engineers, you have to collect images or data set of good and bad images under the expected lighting and optics conditions. So if you want to do the proof concept on an existing system, that means like now you have a system which is capturing like images daily. So actually, that will be much easier for deep learning to actually show the performance or to do the feasibility study. So I think there's two ways. First one is to set up the system, capture the images, and the second one is to use the images for the existing system. And then after that, you just need to select those good images and bad images, around 50 samples for each of them. Then after that, you just dump into our deep learning software, and you can start to label them, train them. So beware about the number of images, because 30 or 50 images normally are good for straightforward applications. But let's say you are looking for difficult application, or you need to achieve 99.9 in the accuracies. So you may need 1,000 images, or maybe it can be more than that. But normally, I think like maximum number of images I did is about 2,000 the most. So this is something we need to achieve a high performance system and to get a good proof concept result. Okay, very good. Any questions? Oh, okay. How small does a defect need to have to be detected in deep learning tools? Okay, so this is a bit subjective, because like deep learning, we can use it for different kinds of application. We can use it for OCRs, present absent checkings, and also we can do it for locating. But these defects, so I will say it will focus on our VD like rate tools, or I will say this is more on the defects detection or cosmetic checks. So I would say this software normally is capable of detecting defects as small as a single pixel. However, defects this size may not be suitable, because most of the time, 1 pixel, it can be a noise or it can be a lighting artifacts. So that is not true. So I would strongly recommend to set your minimum defect size based on the quality of image you provide, and also the actual reliable size of the defects you want to detect. So based on my experience, okay, I can give you some indicator. I wouldn't say this is true for all the case, but nominal should be at least 50 pixels, which is like you can see from the images. So not like, okay, 50 pixels or maybe the dimension you mentioned with your naked eye, because our human naked eye, we cannot measure. Or even though you try to use the calipers to measure, but that is not true, because we should always measure, or we should always define the size based on the images, because the software only interprets everything from the images. So this is how, and also this should be the way we define the smallest defect size you want to know. So this is very straightforward. And I would say for any vision application, the road times always, you need to achieve the best vision system that makes the optics and lighting. We always try to optimize them. Then only we continue with the software. We try to test it, we try to label them. Because always I heard some customer tell me that, so they try to evaluate a project, but they need to do a lot of cycles. That means after they get the first set of data or images, they train the system, the result no good. Then they continue to improve their lighting. Then after that, they found out they need to retrain the neural networks again. Then after they get some result, then they retune the lighting and also the camera again and again. So this becomes a no-ending cycle. So in my opinion, so to make the system or to make the development faster, so always we should consider we optimize the lighting and optics to the best, then only we move forwards to the image collections. So actually this will help you a lot in the development and make the whole process faster. So estimations, normally, I guess it will be 1 to 2 weeks to optimize the lighting and optics, then another 2 weeks to tune the system. So easily for the proof of concept, we have to use like 4 weeks. So, and to define the defect size, that is the time when you have the image, when you have the result, then we can define the size we are confident to detect. So that should be the best way to define. But my comment about 50 pixels, just the indicator for you. So at least you know, oh, 50 pixels. So this is something deep learning can handle. Yep, that's all for this question. Any other questions? Oh, okay, any problem if installed on a vibrations environments? So normally for any vision system, so we strongly recommend not to install in an environment which is more than 2G like vibrations. So there are like different kinds of like ways to gauge the vibration. Normally we use G. So in Cognex smart camera system, so normally we strongly recommend to install the environment in only 2G. Not more than 2G, but actually for some system we tested in 10Gs. It still works, but this is just in our it's a simple dummy test, but it's not the true like test we did in the production flow. So 2G is my answer. So any other? Okay, how stable is these visions? And some visions you need to reteach again, even though with the same product. Yes, because it really depends on your products. Because let's say for the first 3 months, you train the system, actually the system should be stable. But normally in the real world application, we found out after 3 months later, there are some new product. Actually, it's not new product, it's a product from a new supplier. So actually from the image, we can know there are some difference which deep learning never trained before. So that's the time we have to retrain again. So most of the time, okay, it really depends on the application. So let's say for application which you have a lot of suppliers, a lot of different variation in the product, so it will take slightly longer time for us to optimize the system. But let's say you will find out, oh, just maybe 3 months or 1 year later, you start to see this problem, then you can just easily add those images in, then we retrain the system to optimize the result. Then you can see the result like will go back to normal. Okay. So any other questions so far? Okay, no more questions. So I would say that's all, and also very happy to answer like these questions. So those questions are very good, and hopefully this session will really help you to understand how deep learning can help in our smart manufacturing. Thanks everybody, and have a nice day.